This is lecture number 27 of the course ME314 Fluid Mechanics 2. Today, this is the third lecture of this week. We are going to start a fresh topic, boundary layer theory. We already have done the potential flow theory. Today, in the lecture, we will be dealing with the first, we will go into the different classifications of fluid flow, from one-dimensional to two-dimensional, three-dimensional, steady and unsteady, uniform and non-uniform, viscous and inviscid flows, the concept of flow separation, and turbulent flows and laminar flows. And then we have the concept of boundary layer concept, what Prandtl has suggested in the year 1904. And then we will look into the growth of the boundary layer thickness only qualitatively. Let's start fluid flow classifications. One of the way by which we classify fluid flow is whether it is a one-dimensional problem, two-dimensional, or three-dimensional problem. So the decision about, in general, as we know, velocity vector is a function of space and time. But for steady flow cases, it is only a function of space variables. So once your velocity vector is depending upon three space variables, I have put variables in terms of Cartesian coordinate system. You can put in r, theta, and z, whatever, in cylindrical coordinates as well as in spherical coordinates. So when the knowledge of velocity vector requires three space variables, then the problem would be 3D problem, three-dimensional problem. If you need a knowledge of only two space variables, whether r or theta, or whether x and y, so in order to calculate the velocity vector, so that problem would be two-dimensional. So if you need only one single variable, whether x or whether r only, then this problem would be categorized as a one-dimensional flow. So we take some examples. For example, here you have two long, infinitely long plates, and fluid is flowing in that direction. So their direction is x and their direction is y. The geometry is two-dimensional, there is no issue on that, but the third dimension is into the paper. But if you see the velocity profile here, the velocity vector is a function of one variable y, because when y is let's say 0 here, you have a maximum velocity, and y equals to some distance b, you call it zero velocity here. So this problem would be called as a one-dimensional problem, because in order to calculate velocity, you need only one space variable. Similarly, if the fluid flow takes place in a pipe, so this geometry is different from this geometry because this is actually a pipe cross section. So I have taken it a circular pipe, and that x direction is the axial direction, and r is in the radial direction. And we know the velocity profile in such cases, if there is a laminar flow taking place, then that would be only a function of r. So that would be called as a one-dimensional problem. Similarly, if you look at the same thing in a picture where it is a three-dimensional picture, but your velocity profile is only changes with r, then this problem would also be called as a 1D problem. Here you see your velocity profile is a function of two space variable, then this problem would be considered as a two-dimensional problem. And here, if you see this tapered section, then your velocity profile is a function of three space variables. So your x, your y, and your z all are significant here. So they are important in calculating the velocity profile. Then this problem would be called as 3D problems. If the problems are space problems as well as in general, if it is a time dependent as well, then it could be called as unsteady and three-dimensional, because if time variable is also involved. We will look today defining steady and unsteady as well. Okay, so next is steady flow and unsteady flow. As we know, in a steady flow, the velocity vector at each location in this space, the velocity is not changing with the time. So that problem would be called as an steady flow problem. So at all points in the field, the rate of change of velocity is zero. It is means the fluid is neither accelerating nor decelerating at any point in this space. So then we call such flow to be as steady flow. Correspondingly, in an unsteady flow, obviously the velocity changes takes place with the time at a given location in the flow field. So velocity is changing with respect to the time. So it means either the fluid is accelerating or the fluid is decelerating. Then such flows are called as unsteady flow, where velocity is a function of time as well. So, for example, we can take an example of unsteady flow. If we have a flow takes place in a pipe when you open the valve or close the valve, the flow conditions are changing. So, either your velocity is increasing or decreasing. Then such flows would be called as unsteady flows. So, in that case, your velocity at a given location is either increasing or decreasing with time. There is one more classification, what you call it, a uniform flow and non-uniform flow. So in uniform flow, we say the magnitude of the velocity as well as the direction in the dominant direction of the flow is not going to change. Then such a flow is called as uniform flow. So here we are differentiating velocity with respect to the position, with respect to the space coordinates, or I have taken here is an S is in a streamline direction at a given time. So all layers at that cross section would have at a given instant of time, you see all layers would be moving with the same velocity. So they are not changing, I mean, at a given snapshot. But it could be at a different position, there could be a different magnitude. Let's say V2 is bigger than V1, but as we see here at that cross section actually, so at that cross section velocity is not changing, then that would be called as uniform flow at a given instant. So here you see a different velocity, here you see a different velocity. So from this side to this side, if before entering into this diverging portion, the velocity is uniform. But once it enters into this diverging portion, the velocity changes. And once it go again into the smooth channel, smooth pipe without changing the cross section, then once again it becomes velocity is uniform. But in this diverging region, the velocity would not be the same. So here is you see this diverging section, this converging section rather, I'm sorry, it's a converging section, so velocity is increasing. So in that case, velocity is increasing as you move from this point to this point. Then it would be called as a non-uniform flow. If the flow takes place in as streamlines are as concentric circles, so you see these concentric circles, their magnitude even though is same, but their direction is changing. So here streamlines are much closer, so velocity is much higher, and streamlines are much apart, so velocity is low. So that actually is an example of a non-uniform flow. There are several other classifications, like for example, when we talk about the effect of viscosity in the flow. So inviscid flow is a class of flow in which viscous effects are actually insignificant and that are not actually influencing the flow and can be ignored. So such flows are called as inviscid flows. Whereas in viscous flows, viscous effects are important and cannot be ignored, and such flows are viscous flows. So as we know the potential flow theory, we have already taken an assumption of an inviscid flow where viscous effects were not taken into an account. So if you look at the flow over a cylinder, so you see here the at the upstream side, all layers are moving with the same velocity at that cross section, so it's a uniform flow. But once it approaches to a cylinder, and you see at that point the so-called stagnation point where velocity is zero here, and the layers of the fluid moves much faster at the top. So as at theta equal to 90, we know the velocity is maximum. So there is a thin layer at the boundary of that cylinder forms what you call it a boundary layer, or actually it is due to the viscous effects which are dominant very close to the boundary. In that region only. So the region where away from the boundary, which is called as inviscid region, in which viscous effects are not important, so we can apply a potential flow theory to get the information about velocity in that region, or even away from that region as well. But close to the boundary, the region in which the viscous effects are dominant, that is actually the boundary layer. And as we see at some point here, the streamlines actually, they are actually following the contour of the body, but at some point they detach from the contour of the body, and that point is actually called as flow separation. And on the opposite side of the cylinder, we see the reverse flow taking place. And that reverse flow is due to those eddies that these wakes are formed, and these this would be the flow dominantly would be away from that wake region. So we can define the types of flows called viscous flows, which are very much close to the boundary where viscous effects are dominant, and we see later that is actually the boundary layer region. And the flow outside that boundary layer region where viscous effects are can be ignored. We can use the potential flow theory to get the velocity distribution. So this is another classification, viscous and inviscid. So there is another example of the aerofoil section. So you see velocities at the upstream are uniform, and then their dashed lines represent a thin region which is very much close to the wall. And if you see the enlarged view here, so you see the velocity is not uniform, or even there is a sharp gradient takes place close to the wall. So that is actually happening in this boundary layer region. So in viscous flows, as we know, the shear stress is mu times du by dy. So it means the shear force, this viscous shear stress is present, and it is present due to two multipliers. One is viscosity, which is a dynamic viscosity part, and second is the velocity gradient. So if we think such a flow in which is inviscid, so it means the shear stress to be zero. So there are two possibilities: either the velocity gradient is zero, or the viscosity is negligibly small. So in that case, your viscous shear stress would be approaching zero. Then we can treat such flows to be inviscid flow. But in viscous flows, the forces associated with this shear stress are not negligible, and they are actually responsible for the velocity gradient here. So having this is non-zero term, and this one also be some velocity changes takes place in that y direction. So it means such flows are actually called as viscous flows. So we have already dealt this equation in the first lecture of this course. So what is the boundary layer, or more specifically we call it a viscous boundary layer, because due to the viscous effect, actually there is a thin layer that has been attached to the boundary where the viscous effects are dominant, and that boundary layer would be called as viscous boundary layer, or in short we usually call it a boundary layer, but this boundary layer concept is more generic, and we will see it in the later part, that this boundary layer idea, works for not just the velocity field, but it works for temperature field as well as for concentration fields. But right now we are only talking about the fluid flow behavior. So we see this boundary layer idea is due to the viscous effects, the region in which the viscous effect is dominant or cannot be ignored. In that region is actually called as boundary layer region, and the layer is actually the boundary layer in short. One more classification I told you which I have not mentioned here in this lecture, but as we already know, the fluid flow can be classified as either external flow problem or internal flow problem. For example, this aerofoil section in which the fluid is flowing over the surface of that aerofoil, then this would be called as an external problem. So the whatever outside the surface of the body, that is actually the whole velocity distribution is we are interested in outside the external body, outside the external body. So that would be called as an external flow problem. Or if your flow could be like a wall bounded flow, so you have walls here, it could be a pipe or it could be a channel. So you see initially your velocity profile is uniform. Once it enters, then the velocity profile starts developing, and at some stage it becomes so-called fully developed. So we will talk about later about this fully developed. And how do we know that is a pipe flow? Because you see the center line is drawn here. This line in this is actually a center line, so we are talking about the center of the pipe. So what you see here is initially it is a uniform flow, but due to the viscous effects, a boundary layer starts to develop, and on both sides of the wall. So here the boundary layer and both boundary layer meeting at some point, they merges together, and the length of the pipe to which these two boundary layers join together would be called as this length is called as an entry length, and after that we call the flow to be fully developed. So it means as you move forward further, your velocity profile is no more changing as you are moving in that direction. So such a flow is called as fully developed flow. So what you call it, since we are only talking about here the velocity profile is a laminar, I will talk about how it differs in the turbulent case as well. So idea of boundary layer is applicable both in the external flow problem as well as in internal flow problems. Okay, another thing that is the classification, we call it attached flows and flow separation. So in potential flow theory, we see, let's say there is a cylinder and A and C are stagnation points, and B is the point where velocity is maximum, and you see all the streamlines are following the contour of the body. So we call such flows to be called as attached flows. So the region in which the fluid is following the body contour, that would be called as an attached flow. But if you have such a case in which your Reynolds number is high, and we will define later this Reynolds number for this case too. So here A is in a stagnation point, B is the point where velocity is maximum, and at some point here at that, if you draw at an angle of 80 degree from the horizontal, that points, these 2 points are called flow separation point, where streamlines detach from the main flow, and the wake region or separated region is generated. So the eddies are formed. So this is actually the where the fluid flow separates, and we see here the boundary layer is actually formed, and after that the flow separation takes place. And in the later part of the course, we will look into more closely how the velocity changes takes place and how the pressure gradient is present, which is responsible for this separated flow. But for sake of classification right now, for simplicity, we call such an ideal case in which it is actually a so-called attached flow, but in reality we have always flow separation, and it occurs even in your cross-section changes. So if you have a larger cross section and then you have some smaller cross section, and you see the streamlines goes from a higher cross sectional area to a smaller cross sectional area, and streamlines goes bunched together, and at the edges some bakes and some separated regions are formed. So that is actually present both in the external flows as well as in the internal flows. You see that you have a square cross section of a channel that has been placed, so that point is in a stagnation point, and you see at that tip the flow separation is taking place. Or if you have an aerofoil section and you see as the angle of attack increases, so the flow separation, the distance by which the flow separation would be depending upon this aerofoil angle of attack. So we will go into the detail later when we'll talk about external flows in aerofoil, flow over in aerofoil. We will see how the boundary layer, because this is where the flow separation takes place. So the streamlines detached from the body, and on the other side of the body you have a separated flow and wake region, eddies are formed. So that is what is actually called as flow separation. Okay, another classification, what we call it a laminar and turbulent flow, and I hope that most of you have an idea about what is laminar and turbulent, but we now define it more closely. So as we know, laminar means the fluid flow is can be thought of as a parallel flow in which streamlines are parallel, and what we call it a layer flow or a lamina flow. So lamina is small layers when the fluid is flowing in the layers, and as we know that these two layers are never cross each other, so they are always moving in a manner so that they are always parallel to each other. So that's such an ordered fluid motion is actually called as laminar flow, and we have one dimensionless number, Reynolds number, which decides about whether it is laminar or turbulent. So for L is a characteristic length. In case of a pipe flow, diameter is your characteristic length, and it will be called as rho Vd over mu. And rho is the density of the fluid, V is the velocity of the fluid, mu is the viscosity of the fluid. So this Reynolds number is taking care of the whole fluid flow behavior in terms of length is in terms of a geometry. Length is a parameter which is taking care of a geometry, what type of geometry it is. Rho and mu are material parameters, so what material properties are there, they are attributed due to the factor of density and viscosity. And V is actually the nature of the flow, very high speed flows or very low speed flows. So Reynolds number takes care of the geometric part, the material part, as well as flow condition part. So as we know, in case of a pipe flow, when your Reynolds number is more than 2000, so it is no more laminar. So transition regions occur, and after 4000 it starts becoming turbulent, and then at 10,000 it becomes fully turbulent. So this is what you have learned in your FM1 as well. So a laminar flow is such a flow in which fluid layers are moving parallel to each other, and no mixing occurs between the two layers. Such a flow is actually called as laminar flow. Actually, the more closely, if you look at the laminar flow in this called laminar flow regime, what is actually having, you have two types of a momentum associated. Momentum, as you know, momentum is actually the product of mass and the velocity. So if you see the diffusion process, so the molecules of the fluid, they are diffusing from one layer to another layer, and they are occurring at a microscopic manner. So at a microscopic manner, they are moving from one layer to another. So this we call it a momentum transfer. And since this process takes place at a microscopic level, we call it momentum transfer by diffusion. So laminar flow is such flow in which your momentum transfer is by diffusion, what is by diffusion is very high. Whereas momentum transfer, if you take it a macroscopic manner, so what you call it in advection. Advection is when your motion of the fluid is due to the bulk motion, or it means you can see how the two layers would be transferring momentum, because one of the layer, if let's say moving with some high velocity, other moving with some low velocity, even though they have same mass flow rate, but since the velocity is different, so they have a different momentum in different layers. So what they do is they transfer momentum between the layers, and if they transfer in a manner in which there is a bulk motion associated. Since laminar flow is having momentum transfer by the bulk motion, or what you call it in advection, is very low. So laminar flow can be thought of as at a microscopic level, a lot of mixing is taking place, but at a macroscopic level, layers are not going to mix. So you can identify each layer. So once you have such a case, then there is some pressure distribution and velocity distribution. So once at a macroscopic level, the pressure and the velocity would not be changing with respect to time. So that is what the important concept of, because at different position you have different velocities and different pressures, but at a given location the pressures and velocities are not changing with the time, because here velocity is different, here velocity is different, because here the velocity is accelerating, fluid flow is accelerating. So we call laminar flow is having a low momentum transfer at a macroscopic level, that is by advection, and high momentum transfer at a microscopic level, what you call it a diffusion, because diffusion always takes place at a microscopic level when molecules diffuse from a higher concentration region to lower concentration region. And you know from your college, from schools, the so-called Graham's law of diffusion. So here advection is actually the bulk motion, and we will see later convection is actually the combination of advection and conduction, which is actually, you will learn more all such things in heat transfer course. So now can you think of the how we can define turbulent flows, because how we have defined laminar flow, the turbulent flow would be defined in an opposite manner. So you see, for example, this smoke coming from a cigarette, that is initially all the layers are parallel to each other, so there is no chaotic motion, and the layers are parallel. Then this region is actually called a laminar flow region. And once the flow becomes chaotic and the mixing takes place, and then what you call it, that region to be called as turbulent region. Similarly, you see in the aerofoil section, most of the region which is inviscid, away from the boundary, and other than the separation point, or other than the wake region, that would be laminar, but the rest, the other one is from after separation point, it becomes turbulent. So layers transfer momentum at a macroscopic level, and you can see that momentum transfer and that mixing. So what we defined turbulent flow is a chaotic flow, and where mixing of the layers, fluid layers occurs, and velocity is fluctuating, and since the laminar flow is some having low Reynolds number, so correspondingly turbulent flow would having a high Reynolds number. And we can see easily opposite to that, in laminar flow you have high momentum transfer by diffusion at a microscopic level. Here you have a low momentum transfer by diffusion, whereas you have high momentum transfer at a bulk level, at a macroscopic level. And obviously due to that the distribution of pressure and velocity also changes, and layers are going to mix with each other. So that is how you should define the laminar and turbulent flow. I mean, probably at an FN1 level, you have seen the laminar flow is when lines are parallel, but it's fine. But now you look at more closely how the different layers of the fluid transferring momentum. So once they are transferring momentum at low momentum at the diffusion process at a microscopic level, and that is actually a feature of turbulent flow, whereas high momentum transfer by advection takes place at a macroscopic level. So that is what we call it a turbulent flow. The question comes, if you look at the flat plate, so you have a flat plate, initially fluid flow is uniform, and then what happens is, due to the viscous effect very much close to the wall, I mean this boundary layer I have drawn here is quite big, but actually it should be very small. So initially your fluid flow in that region close to the wall where viscous effects are dominant, the streamlines are somewhat parallel, and there is certain velocity profile associated in that region. We call it a laminar boundary layer region. And after certain distance, as the fluid moves in the direction of the flow, that is along the length of the flat plate, some of the layers close to the wall are still parallel, but as you go away from in the y direction within the boundary layer, then there is a mixing and eddies formation takes place. So that region would be called as turbulent flow. And laminar to turbulent doesn't occur instantaneously, or there is certain region, what you call it a transition region, where transition takes place from laminar regime to turbulent regime. So what we see here is the behavior of the fluid flow is different in laminar, different in turbulent. So we have seen here, if you look at the velocity profile, so you see that this is a bigger thickness in that region. In turbulent region, your thickness is much bigger. So we actually divide the whole turbulent region into when your after your length at which the flow becomes turbulent. If you look at the velocity profile, we can see this is a no-slip boundary condition. So layer of the fluid which is sticking to the wall would be having velocity 0. And in that very thin region close to the wall, that would be called as viscous sublayer, where the flow is still laminar. And then you have a buffer region. So at this vertical distance, some transition takes place, and then you have a fully turbulent core of that region. So main core is turbulent, but very much close to the wall. So these layers are called viscous sublayers, buffer layers, and turbulent layers. You see, if you look at this concept of momentum transfer in laminar and turbulence. So you see, let's say for example, before turbulence, when fluid is moving in a laminar region, you can identify at a macroscopic level each layer distinctly. So the layer at the bottom is marked with letter 12, and the layer above that would be marked as 7 and 5 and 2. So we can see the fluid flow is taking place, and each layer can be spotted so that it moves somewhat parallel to each other, parallel to the neighboring layers. So that would be the behavior in the laminar region, what you call it before turbulence. But still what is happening is this is a bulk motion. So there is no momentum transfer at the advection level in laminar region. But still within the 7 region, the molecules are moving here and there very fast. So there is a very high momentum transfer within that 7 region. But from 7 to 5 and 5 to 2, there is very less momentum transfer. That is the feature of the laminar flow. Whereas in turbulent flows, we are interested in high momentum diffusion at the macroscopic level. So your momentum transfer, because the layers would be chaotic, and this top layer is here at the bottom, or this 12 layer is gone up somewhere here. So this is actually happens after turbulence. And we can see this 3 different layers we already have defined as viscous sublayer, buffer layer, and turbulent layer. And in this turbulent region, most of the flow is within this boundary layer is having full of eddies. So mixing is because a lot of mixing takes place due to those eddies. But the layers which are very much close to the wall, viscous sublayers, would be somewhat following this laminar profile. But the layers above are different. So we can characterize laminar turbulent flow. So the region in which, for example, along the length of the flat plate, the length of the flat plate to which it is laminar, it is, and after that length it becomes a transition or it goes into turbulence. That is actually called as critical length. XC is called as critical length, and we will see it later. Okay, if you see the velocity profiles, we know within the boundary layer, this is a no-slip condition. Both having laminar and turbulent have no-slip condition, but close to the wall, you have some profile which velocity gradient that is increasing. But once you calculate that velocity gradient very much close to the wall when y approaches 0, so you have some lesser steep gradient. But here if you see, the turbulent flow is such where a lot of things have been taking place in the core, which is full of eddies, but close to the wall there is a very sharp gradient. And we will see here the velocity is a local velocity and here is an average velocity. So actually the turbulent flow is can be thought of as, because turbulent flows are unsteady flows, so they are time dependent. So what I do is, your velocity is a function of time. So somewhere you have higher velocity, lower velocity, the velocity is fluctuating. So what you call it an average velocity is somewhat where the dominantly the trend for the velocity as a function of time, that velocity is following. So that velocity is called as. So what we do is we actually divide the flow region into 2 parts. One is average velocity component plus some fluctuations, which could be in positive or which could be negative. So that would be some function of time. So that is a fluctuating part and that is an average part. So your local velocity is a combination of average velocity plus the fluctuating part. So whenever we draw that velocity profile, so we are talking about the average of the velocity, because in turbulent flow velocity is a function of time. So we are not talking about the fluctuating component. So we are only talking about this in this drawing that velocity profile and calculating that velocity gradient. We are only taking into account this average component of the velocity. And the same thing happens in the wall bounded flows, because we have seen the example of a flat plate which is an external flow, and if it is a wall bounded flow, then you see there is a velocity profile, and if it is laminar, then you have a perfect parabolic velocity profile. But if it is something like turbulent, then you have some steep gradient, and you see your actual velocity component would be some function of time which is not stable, but your average velocity is some smooth curve. So that would be different velocity profiles are present in different flow regions. In laminar, you have a different velocity profile. In turbulent, you have a different velocity profile. And this is how we distinguish two different types of flow regions, whether it's a laminar or turbulent. Okay, what Prandtl has done in 1904, he has actually divided a fluid domain into two parts. One is the part which is very much close to the wall or the solid boundary, where viscous effects are dominant and there are velocity gradient present. That region is called as boundary layer region. So that is, I have drawn it with the dashed lines. And that is a flat plate. So initially your velocity profile is uniform, but once it approaches to the solid body, and due to the viscous effects, the layer of the fluid which is very much sticking close to the solid boundary is having very high viscosity. So because of that, the layer is not moving. But as you go up in the y direction, the layers having different velocities, and velocity changes takes place, and the region in which in that region velocity would be some function of x and y, so it would be a two-dimensional flow. And delta is actually, x is this length along the length of the flat plate, and delta is actually called as boundary layer thickness. So when you are x here, you have different boundary layer thickness. When you move here, you have a different boundary layer thickness. So this is actually a concept of growth of the boundary layer thickness. So what Prandtl has done, he says the whole flow field can be divided into two regions. One region outside the boundary layer region, we call it an inviscid region. So where the potential flow theory works, and the region within the boundary layer, it is where viscous effects are dominant, that is called the boundary layer region. And outside the boundary layer region, we call it where the viscous effects are not dominant, and the fluid flow can be called as inviscid fluid flow. And if it is irrotational, then we can use the potential flow theory to get information about that inviscid region. So what Prandtl has suggested, that different theory to be applied for the flow field where the velocity changes are taking place, where viscous effects are not dominant. That would be called as inviscid flow theory or boundary or potential flow theory. And the region in which the viscous effects are dominant and the velocity gradients are present close to the boundary, that region would be called as boundary layer region. As we see in the flat plate, you have initially uniform flow, so all packets of the fluid would be having no distortion. But once it is close to the boundary layer, then the velocity changes takes place. But still they are parallel in this laminar region. And then there is a transition, and then there is a flow becomes turbulent. So velocity changes takes place, and the region outside the boundary layer, no velocity changes takes place. So fluid particle is experiencing no distortion. So that would be region as where the potential flow theory is applicable. In the region in which velocity gradients are present, that region would be called as boundary layer region. And so the potential flow theory is not applicable in that region. This is what the Prandtl has suggested. If you look at this growth of that boundary layer thickness, we have already talked about that as you are moving along the length of the flat plate, this boundary layer thickness is changing. So it is something not constant. This thickness is not a constant value, but it is something, a variable which changes along the length of the flat plate. So the question is how your laminar and turbulent boundary layer thickness differs. So once you are in the laminar region, your boundary layer thickness is smaller, but you have some higher boundary layer thickness in the turbulent region. So when you go into the turbulent region, your boundary thickness grows much faster than as it grows in the laminar region. And we will see it mathematically in the later part of the course. Okay, so if you see this flat plate, there is at very low Reynolds number, let's say 0.1. So there is a region away from the boundary where viscous effects are away from the boundary, viscous effects are not dominant. Where close to the boundary, the viscous effects are dominant. So that is something happens at the low Reynolds number. If you increase your Reynolds number, let's say from 0.1 to 10, then you see the region in which the viscous effect dominant has shrunk down. and your velocity profile also changes. And if you look at because this viscous boundary layer, so as you see initially you have streamlines, and streamlines are deflected away from that surface. So it is because of that boundary layer. So once you increases your Reynolds number, then deflection also decreases. So if you further increase the Reynolds number, let's say 10 to the power 7, then we see that your boundary layer thickness is much smaller. So that region would be as your boundary layer thickness, which is we can think of the streamlines are actually not deflected or very slightly deflected, because that thin region has been very close to the boundary at high Reynolds number. So the formula actually how the linkage between boundary layer thickness and Reynolds number is that your boundary layer thickness is inversely proportional to Reynolds number. So if you have higher Reynolds number, then smaller the boundary layer thickness. So that is we have seen it today in this lecture qualitatively, and the same thing we will do it quantitatively in the later part of the course. Okay, very small problem. Let's say you have a small insect that is placed at point 0 here, and that is actually the region inside the boundary layer, as that is being shown in this figure. So what the insect finds, the velocity at that location is too high. So here the insect is placed, and the insect finds that velocity is too high. So, and obviously this insect is going to take a one step, and keep in mind that the insect is so small that actually it is not disturbing the fluid flow. So the possibility for insect to move either in the direction of 1, or in the direction 2, in the direction 3, or in the direction 4. So take a pause and try to answer where actually it should go from these 4 possible directions. It is initially placed at 0, because right now at 0 it is the insect is feeling very high velocity. So insect has to move in a region obviously where the velocity is low. So as you see the thickness is growing in the direction 1, or if it is goes in 3, the thickness is changing. As it is going above, you see its velocity is increasing. So the only way by which the velocity is decreasing would be if it is goes in the direction of the 4. So you can see there is a significant velocity drop, and once y approaches 0, then the velocity would be 0 here. So if insect wants to be happy with the position where the velocity is lower, then insect has to move in the downward direction, because the velocity at each location there is certain velocity profile, and the velocity profile at that point is such like that the velocity is increasing. So if it is goes in 2, the velocity is increasing. If it is go in the 4 direction, the velocity is decreasing. So that is the answer, and this is where I finish today's lecture.